Imagine an EV battery pack traveling from the scorching heat of a desert highway to a freezing mountain pass, while an aerospace control board endures pressure changes, vibration, and moisture at 35,000 feet. In environments where electronics have no margin for error, reliability isn't just a design goal, it's a survival requirement. And the technologies that protect these systems are evolving faster than ever. Welcome, or hopefully welcome back to the Reliability Matters podcast, the show where we discuss reliability-focused best practices, strategies, and emerging technologies within the electronics manufacturing industry. Today, we're diving into several of the most critical challenges facing modern electronics manufacturing, protecting electronics and battery systems in harsh environments, advancing thermal interface material technologies, improving precision dispensing and coating processes, reducing waste through automation and robotics, enabling scalable manufacturing through calibration, and adopting more sustainable and eco-friendly coating approaches. That's a lot to take on in one episode. So joining me is Jon Urquhart, Director of Global Applications Engineering at Precision Valve and Automation, better known as PVA. Jon spent more than 30 years at the forefront of fluid material processing, specializing in dispensing, precision coating, automation, and custom system development. His work spans mission-critical sectors including aerospace, electric vehicles, medical devices, semiconductor packaging, and advanced electronics assembly. Jon brings deep experience in overcoming the environmental and thermal demands placed on modern electronic systems, the process controls required to achieve repeatable and reliable material deposition, and the role automation plays in eliminating human error and material waste. He's also a strong advocate for a collaborative model that brings vendors, manufacturers, and lab technicians together to accelerate processes, improve reliability, and reduce costs. In this episode, we'll explore how emerging materials, advanced dispensing technologies, and smarter automation strategies are reshaping reliability from the lab to the factory floor. And it all begins right now. Let's get started.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Hey, Jon, thanks for being here today. I'm looking forward to our conversation.
Hi, Mike. Thanks very much for having me. That was quite the intro.
Well, you've got quite the storied career, Jon. Have you been in the industry? I know you've been with, I think, PVA 30 years, right? Is that right?
Yes. Since
did they hire you out of grade school, or what happened?
Yeah. I met Tony Hines, the owner of PVA, when it was just in an incubator center, and started when there was just a handful of us, and dove right into the electronics industry, learned a lot of what I know today just from paying attention to processing, dealing with people like yourself, learning from others, and just trying to be as much of a sponge as I could.
I would think this is a good time to be in the dispensing world with electronics the way they are today. I mean, it's always been a value added, right? It's always some degree of requirement to do some type of dispensing, whether it's conformal coating materials or heat dissipation, thermal stuff, or whatever. But it seems to me, maybe because I'm in the cleaning world and I see the world through the lens of clean or dirty, and I know how important clean is to many types of adhesion processes common in dispensing. Maybe I'm just looking through a filter. But it does seem to me that there are more applications today on a wider swath of assemblies and applications that are requiring some type of material to be dispensed onto the assembly. That does seem to be a growing industry. I don't know if it has to do with miniaturization or more boards deployed into harsh environments or combination of all these things, but Certainly, I've seen it explode in
Right.
not just one application, but numerous applications. Do you share that view?
Yeah, absolutely. Let's take a look at, automotive, just that sector alone. Look at all the electronics that are in vehicles these days, whether it's drive-by-wire, engine control modules, all the different sensors, in cabin, not just around the engine ecosystem, but, in cabin monitoring, passengers, seat systems, entertainment systems, Wi-Fi, everything else. A lot of electronics, a lot of exposure to environment, and they all need to be, protected, bonded, glued in some way, shape, or form that, allows them to operate, throughout their entire life cycle.
I have two cars, John, that I drive regularly. One is my, fairly modern, big giant SUV with all of the electronic systems, the ADAS systems that keep me safe, and infotainment systems that keep me entertained, and all of that. And then I have a 1968 Mustang. And I like to compare the two in terms of reliability. If 100% of the electronics failed in my Mustang, not the electrical system, but the electronic system, the only thing that would fail me is I wouldn't be able to listen to my crappy little AM radio, in-dash radio, because that's the only electronics in the car. If some, maybe even one, depending on the one, of the electronic systems fail in my modern car, that could be my blind spot indicator, or my collision avoidance system, and or my adaptive cruise control. In other words, I could be seriously injured or worse if any of those fail. So, I think the benchmark for reliability now is far higher, because we're no longer being entertained or massaged in our seats with these electronics exclusively. We're now being kept safe with these electronics, and we rely on them way more than we used to, right?
Right.
We assume that they're accurate. If the light's not flashing in your mirror, make the lane change. Forget looking over your shoulder. As we were trained when we, 100,000 years ago when we learned to drive.
Right. Yeah, the trade-off is, that hopefully all the electronics don't make us complacent in paying attention to when we're driving, right? You still want to make sure you look over your shoulder occasionally. Make sure to look.
They do make you complacent. Yeah.
Right. But you want to remember that it's still a hunk of metal flying down the highway, so you want to make sure you're in control.
Yeah, and I got 7,000 pounds of metal moving down that highway at who knows what speed. What are the most significant environmental stressors? I talked about harsh environments a little bit earlier, and miniaturization and all that. But what are the most significant environmental stressors that threaten electronics and battery systems specifically, and also in aerospace and other EV type applications? And how do they influence material and process selection?
Right. Yeah. So, a lot of the main risks are everything we hear about in, electronics, moisture, humidity, temperature, thermal cycling, mechanical shock and vibration, stresses, and then you've got, all of the random dust and particulates, in the environment that, electronics are in. Some need some, extra chemical resistance, if maybe they're in splash zone or under hood for automotive, for example. And then, with a lot of, space vehicles and satellite and whatnot, now you're paying more attention to radiation exposure, different levels of environment that we're not, traditionally used to. And then even beyond that, abrasion resistance in some cases. If you've got, an LED panel or a solar panel or some sort of module that's out in the elements, it needs to sustain, impact, or, even if it's in a enclosure and a technician needs to do a service or rework or something, you want to pay attention to those sorts of end use environments to help you, pick what sort of method or product you're going to use to protect.
You talked about radiation, and boy, you are right in the news right now. Not you personally, thankfully, but that topic is in the news. Airbus having to provide emergency repairs to their newer A321 fleet of aircraft due to radiation exposure on some of the electronics. And they're writing some software patches to mitigate that. I'm not quite sure how software fixes, a board issue, if it is indeed a board issue. But at any rate, Boeing tried that a few years ago with the dismal results. I mean, fatal results. But at any rate, that just goes to show, to back up what you're saying, that there are very severe environmental stressors. Now, radiation has always been there, vibration has always been there, moisture has always been there. I think what's happening is the tolerance for all of these things has been severely reduced due to probably primarily miniaturization. And, some might talk about frequency and, signal integrity, stricter signal integrity requirements, things like that. But certainly we've changed the game. The world hasn't gotten any worse in terms of its attack on electronics, but certainly electronics have become way more sensitive and less tolerant to residues and to moisture and to other factors due to miniaturization, component density, lack of any clearance between the laminate and the component material, and all of the knock-on effects.
Right. Assembly tolerances, all that.
Yeah. How do you balance, or how does one balance the need for robust environmental protection, such as moisture, salt fog, and temperature extremes, with weight, cost, and manufacturability requirements? I mean, this is this is a classic example of on one hand, on the other hand. So how do you see your customers balance that fight between reliability and costs and manufacturability and things like that?
Right. Yeah. What process do they choose? What materials do they choose? It's, a lot of it's about, the designers and the manufacturers, truly understanding what's the end use environment. Like you said, the environments haven't really changed so much. We have moisture, we have vibration, we have shock, and all the other things that go along with it. But it's really understanding, is this going to be a product that needs to operate inside your house? Does this need to operate on a highway? Does it need to go up into space? Whatever. So it's determining the level of protection you're looking for, and then balancing that with, manufacturability, costs, type of manufacturing process, speed of manufacture, supporting costs, things like that. When it comes to protection, you've got, your three main, liquid applied methods. You've got your thin film conformal coatings. They're lightweight. Most are easy to repair, low mass, can be applied very selectively, low viscosity, so on. And then you get into like your encapsulants, a little bit thicker viscosity, thicker layer, so you might be above the 200 micron, 150 micron to, let's say, 500 to 1,000 micron for encapsulants. These will offer, greater level of protection due to the thicker layer or the types of materials that might be used there. And then you get into potting materials where you're filling an enclosure with electronics inside of it. And, now you've got, a much larger, heavier mass of electronics that may provide all of the protection that you're looking for. It's very durable. You can drop it out of a moving vehicle. It's still going to run, but it adds a lot of mass. So there's a trade-off between, what each of these processes, and the chemistries associated with them can provide as far as protection. And then, as, equipment providers, we see people that also implement kind of hybrid processes where you may use a thin film coating to provide your general protection from the moisture and so on. But then, a secondary operation could be employed where you might do maybe a selective encapsulation for maybe a high voltage area, or larger components that maybe are susceptible to shock and vibration. Or you might even, look at doing like a staking, dispensing operation to, stake or bond a component to a circuit board.
Interesting. I wasn't planning on asking you this, but if you'll indulge me, out of just morbid curiosity from me, in a very oversimplistic description of any kind of dispensing equipment, let's just call it, batch dispensing equipment as opposed to inline, just to make it simple. There's a certain element that's common to pretty much all brands, and that's this XY component, right? You have to be able to dispense in a very specific location. So there's X, Y, Z axes that we're all dealing with, and there's a certain technology behind that that's pretty mature. I would think what defines one brand over another, without getting commercial here, but it is really in the dispensing part of it, not so much the XY and all that, because everyone can do that, but in the actual needle, in the nozzle, in the valve, whatever the case may be.
Right.
Yeah. PVA, I mean, the name of PVA is precision valve and automation, right? So it seems like PVA's roots are in the actual dispensing, and quite literally the dispensing, not so much the XY and all that stuff, but that comes with the territory, obviously.
Sure.
Are there major differences, without jumping down a commercial rabbit hole, but are there major differences within the technology of the actual dispensing nozzle, if that's the right term, or is it just a high pressure line and a small orifice that's pushing this stuff out? I would assume there's some science behind that.
Sure. Well, it all kind of depends on what sort of process you're talking about. So, let's start with conformal coating, for example. You've got 4 main applicator types. You've got atomized spray. You've got your airless or film coating type spray. You've got needle dispensing, and then you've got, jetting, which is, firing, dots of fluid, towards a substrate. Each of these have their pros and cons. Atomized spraying allows kind of the widest range of viscosities that are applicable through atomized spraying. Airless applicators tend to be more limited in viscosity that can be used, often with a lot of solvent-based products, but they can apply at very high rates, high rates of speed. Needle dispensing is needle dispensing. You are forcing liquid through a nozzle, but coupled to that, might be some sort of metering device. And, that's another rabbit hole. There's no one size fits all metering device for all of the different fluids that are out there. You've got, we'll say 4 of the main technologies used in a lot of our, across our industry today. You've got gear pumps, progressive cavity pumps, rod and even piston style, displacement systems. And then, with jetting applicators, and, then you've got, really, you're limited for, nozzle size. Sometimes it's type of fillers that can be used in some of the materials that you can jet. They could pack up or separate or compact or shear. But yeah, so going back to how this all started with your question, a robot's a robot, right? There's no extreme rocket science there. Yes, there's different types of robots and different types of slides and motors and mechanisms and sensors. When it comes down to the valves, at least for us, when we started out, we saw a lot of advancement and development in 100% solids conformal coatings. And while atomized spray technology had existed for many decades prior to that, we looked at this and found a way to kind of fine tune and develop, how cleanly these types of materials could be applied to electronics, in particular. And that's really what kind of kickstarted us in the electronic space.
I love to talk about failure modes. What failure modes do you most commonly see when protective coatings or encapsulants are improperly selected or
Yep.
inconsistently applied?
Yep. Well, bubbles, always the big one. And if you see bubbles, show up, you want to take a look at, is it something, or are they appearing on top of components or on top of the substrate, maybe in unpopulated areas? Or are they appearing around your components, maybe clusters around leads or something like that? So, look at where they are occurring, and then that can lead you to what might actually be causing them. If it's around a component, then it can be trapped air. It could have to do with maybe the application or type of applicator used or the speed of application. It could be how fast the products are being cured as well. You could have an air pocket trapped underneath, and maybe too hot, too fast causes that bubble to expand and then pop out of there. Then if you see air bubbles or fish eyes even shown up on like an unpopulated area of a substrate, then take a look at, is it maybe spray pressure, turbulence due to application speed? Take a look at, is there moisture in your fluid reservoir? There's a number of different things to look at to try and fine tune or hone in what might be causing a bubble issue. Some of the other things, we might see, you might see cracks, for example, if you apply, too much coating outside of what its normal, recommended range is. Keep in mind, more is not always better, right? And, in some cases, you might not see it just in normal day-to-day use, but, you see cracks appear maybe due to thermal cycling combined with just too much thickness of a particular coating. And then you've got, de-wet, which is probably something that, you see in your space quite a bit, due to improper cleaning or not enough cleaning or the wrong type of cleaning, or surface residues, maybe unreacted fluxes or some other upstream process that hasn't been cured properly. Or then, de-wetting often can happen, due to the infamous popcorn day, or Cheeto dust, on people who have been handling the electronics. So another, condition is de-wet, which, oftentimes caused by, probably improper cleaning. This falls into, a lot of what you see, Mike. I would imagine in your world, you want clean substrates for coating or bonding, right? And, there's could be some residues left over, whether it's flux, unreacted, adhesives or fluxes from upstream in the process. And then, you've got other factors such as, the infamous popcorn day on the production floor. And,
popcorn's good at the movies, not on your production floor.
Yeah, exactly. Two things that electronics do not like are salt and moisture or oil. So, you want to make sure substrates, I always say substrates need to be clean. And then, other things, delamination is something you may see caused by poor adhesion oftentimes, where you have the cured film may separate from the substrate due to poor bond. And then, less critical things may just have to do with what the surface of the coating looks like. Does it have a matte finish? Is it kind of wavy and, what we typically call like an orange peel surface? Not usually as critical, but, if this happens, it's worth investigating just to make sure it's not something else that can lead to a worse issue down the road.
Sure. I've seen, we talked about the rise in dispensing applications and the need for those on modern circuit assemblies. One of those dispensing applications are thermal interface materials, or TIMs. What challenges arise when applying a high viscosity? I think these materials are generally pretty high viscosity materials, And how does automation ensure consistent bond line thickness and thermal performance?
Right. So yeah, a lot of the TIMs you're talking about, often referred to as your one part pre-cured gels. These are in the paste million centipoise and up sort of viscosity range where you almost can't really measure it. It'll move when you apply pressure to it, not necessarily shear thinning, but it is dispensable, but then it just kind of sits there, kind of like a liquid pad, for example. So, these TIM gels and gap fillers, they typically have high amounts of abrasive fillers, whether it's aluminum oxide, some might have ceramics in them, some might have glass beads, and they're all abrasive. So, if you aren't using the proper fluid dispensing system, valves, fittings, so on, it can lead to issues. So, you want to have a lot of, use components that are wear resistant, maybe carbide based components inside your dispensing valves and pumping mechanisms that are wear resistant. You want to take a look at, the pathway of flow, hoses, fittings that use minimal restrictions to provide smooth flow of the materials, all the way out to the dispensing nozzle itself. And the reason why we want to look at flow paths, you want to make sure, you're not shearing any of these thermal materials so that you're not actually changing the properties of them by the time they get dispensed. When it comes to the automation aspect, the robots, provide consistency and repeatability of the dispense pattern or the dispense volumes of material that are applied to these to your target locations. Sometimes we see issues even just around dispense nozzles being used with certain TIM materials, and looking at finding the proper ratio of dispense nozzle to dot of thermal material you need to apply. For example, you might have a very smooth surface plateau on a heat sink that you need to apply a very small dot of thermal material. But you can't get it to break off of the nozzle because it's not, the green strength doesn't allow it to kind of wet and stick there just enough to pull off. So, you want to, pay attention to using the right nozzle ID to get it to shear right. And then also, maybe add in some motion from your robot to get it to break cleanly and consistently every time.
Jon, you'll be happy to know I learned a new word for this next question. I actually had to look it up because first of all, I had to learn how to pronounce it properly because it's tricky. Maybe you'll know the word. You'll certainly know it out of this question. How do material properties such as viscosity, trixotropy, and if I'm pronouncing that, trixotropy, am I pronouncing that right?
Thixotropy.
Thixotropy.
Thix. Yep.
Oh, so it is. Yes. Thank you. Now I know the word. So I didn't quite learn that new word. Trixotropy. And cure behavior influence the choice between jetting or needle dispensing or selective coating or full encapsulation.
Yep.
How does that get determined?
Well, let's look at just fluid viscosity, on its own. That kind of leads you to determine if you're going to be applying, a thin layer like the conformal coatings, if it's, very low viscosity. If it's medium or high viscosity, then you might be looking at more of an encapsulation type process, because the material's got more body. It's going to sit thicker. It's not going to wet out as much. And you have that, that larger film build. Your high viscosity fluids retain the shape after being dispensed. So, these could be used for creating dams or defining the shape of the area that you are encapsulating. When it comes to choosing whether you're going to be, jetting or needle dispensing or spraying even, then you kind of take a look at, what is the size of the area you're looking to protect. So let's take a flex circuit, for example, whether it's in a mobile device, medical device, antenna, whatever it is. And it could be a very small assembly, but it might only have just a handful of, say, surface mount components that need to be protected. In a case like this, you might only need to protect the component itself, or maybe even just the solder joints alone. And this is where maybe a jetting method would come into play, because you can, apply these very fine, precise dots of fluid. If you are then looking at a design, say on like a traditional circuit board, much larger, say, something in an engine control module, for example, then you might be looking at, spray valves to apply a protective layer, thin film protective layer, or wide area nozzles to cover larger areas of encapsulant. In some cases, you might use a combination process where you might have a spray valve covers the larger area of the assembly, and then a dispense or a jetting valve to apply coatings or encapsulants in finer or detailed areas, or even borders.
What process variables most commonly introduce variations in dispensing or coating, and what engineering controls help maintain repeatability?
Sure. So, viscosity fluctuation, changes in fluid pressures, which lead to flow rate changes, or even changes in substrate location or heights. All of these, a combination of these things can lead to, irregular patterns or changes in thickness and outcome. Again, we'll start with viscosity again. If you're looking at coatings, for example, oftentimes, you'll see a fluid delivery system that might have some sort of metering added to it, but might also have a heating feature that can stabilize or even lower viscosity to maintain, maintain consistent viscosity throughout. If you have a system that might have some pressure fluctuations that, obviously lead to, flow rate changes that cause an inconsistent pattern, dispensed pattern, then, you want to take a look at what you're using to regulate the fluid pressure. It could be just having proper controls added to monitor and adjust, or adding a metering system again, within the fluid delivery, system to control and minimize those sorts of variations. Other tools added into the automation, might be a weigh scale, for example, inside the dispense area, where you can do a dispense check and then closed loop feedback to monitor or adjust, the dispensing nozzle or the metering system to stay on target for what sort of amounts you're looking for. If you were talking about the substrate itself, I mentioned, variations in heights or location of the substrates. Then you want to employ things like fiducial cameras, obviously, height sensors, whether it's a touch probe or a laser height sensor, and these tools combined help find the substrate in X and Y and correct for skew and placement. And then, also adjust for Z locations and topography changes so that, your dispense locations and your dispense heights or paths can dynamically adjust based on where these substrates end up in the system.
Yeah, some of that answer actually partially answers my next question. Talking about the differences between automated dispensing systems and manual dispensing systems, or maybe semi-automatic dispensing systems, there are some obvious, I'm a layman in terms of that. So, I can think, okay, you're going to get if you need a straight line, you're going to get a straighter line if it's automatic.
Sure.
You probably get a little bit, a lot of improvement on the volume of deposition and things like that. What are some of the other differences, maybe a little bit less obvious, that provide improved performance in automated systems versus manual systems that maybe someone sitting on the fence might not appreciate at that point in time, and particularly for mission critical electronics?
Right. So, anyone who's ever worked in a lab and they've been tasked with trying to create some outcome, maybe has tried doing some sort of dispensing, by hand and said, look, I did it one time. Now you have to duplicate that thousands, if not millions of times over, that gets tough to do by hand, by one person, let alone even a small army of people that can do it. So, now you move up to the automation, and the automation itself, as we mentioned earlier, very trivial at this point. There's automation of all sorts employed globally. But then it's understanding the combination of fluid delivery, the fiducial cameras, the height sensors, needle calibration, fluid calibration, weigh scale calibration, pulling all of that together to keep a process on track, right? Robots are great at they can perform tasks, millions of times over, high repeatability, very accurately, very consistently at a generally a known cadence, for example. So it's very predictable when everything's running right.
Right.
When you're doing it all manually, sure, you can provide a manual based dispenser that is has some metering technology to it, so you displace the same amount every time. But then the motion component and the alignment component is where a lot of the automation and these sensors come into play. And then you can go down a whole rabbit hole about inspection and closing the loop there and feedback and finding errors and things like that.
I'm going to qualify this question because the answer could be wide, depending on the context. In high volume applications, where do you see the largest opportunities for reducing human error through automation? Now that answer might be different depending upon whether it's a TIM or conformal coating or whatever.
Sure.
But in general, I guess one of the ways to ask the question would also be, what are the most common mistakes humans make that automation mitigates? Right.
So, we've been talking about robots and sensors and vision and everything else. And, a lot of it is understanding, the end goal and tailoring that aspect to it. But then, a lot of what people don't understand is the handling aspect with substrates. You can feed it into the machine, but then what, right? So it comes out of the machine, maybe it goes into maybe an inverter and you coat or do a process on the second side of it. Then it might go to a curing oven. And then it's got to go after curing to its next assembly stage. But within all of that, if you don't have, whether it's, proper alignment or leveling of equipment, if you don't have, clean fixtures, if you're doing a lot of manual handling, then, it opens up a lot of the things we talked about earlier on failure modes with like fingerprints, uneven, we'll use coating as another example, uneven coating if maybe the substrates are just laid on a bench or not racked properly, things like that. In high volume, you look at employing all of the checks and balances in the automation, again, the vision, the sensors, the metering, and having all those work together to keep that aspect of it on track. But, don't lose sight of the fact that beyond the dispensing step, what has to happen next? And is it handled properly, between those steps as well?
A lot of companies these days are chasing one of two greens. Maybe green from an environmental standpoint, sustainability programs, for example, or green cash, or both, probably both.
Right.
How can automated dispensing systems significantly reduce material waste, especially when working with high cost or environmentally sensitive chemistries or other ingredients?
Mm-hmm. Well, there's a couple ways to achieve that. Let's start with how the adhesives or coatings are applied. Make sure the automation is set up to apply where you need it to go. If you're doing a conformal coating process, just because you can spray the whole thing from end to end doesn't mean you necessarily need to or have to.
Right.
Many automation systems can be very selective. So be sure that you understand, how to program properly, and can I keep it within the boundaries of the product that you're trying to protect, so that now you're not spraying outside the boundaries and spraying, so you have adhesives or coatings inside the robot. It's just wasted material at that point. If you're working with, for example, two-part, reactive materials like potting and encapsulants, take a look at, how we optimize the flow path and the types or size of the mixers used to minimize the volume of mixed material that's in process. What this does is this avoids excess purging and wasting fresh material just to keep the process running. Beyond that, pay attention to the maintenance schedules and performance of your valves or the applicators over time, and check for leaks, check for wear. Be sure to follow the recommended maintenance from your equipment suppliers, and rebuild and replace any components that are leaking or look like they're causing a failure of some sort. That alone leads to a lot of wasted material. Or just even poor results in the application, because maybe a leak in a valve is causing a drip or a tail of material to land in a keep out zone.
Yeah, I would think another in terms of not over applying where it's not needed. Whatever, let's say it's conformal coating. Let's say a certain section of the board should be protected, but other areas don't need to be. One might say, "Oh, just spray the whole thing," but you're also limiting your rework opportunities later in life, right? So if it doesn't need it, don't put it there, because you're just keeping your options open if something needs to be replaced later. Just a couple more questions, because we're starting to run out of time. What does effective vendor manufacturer technician collaboration? I know in your bio I read that about you, that you're into getting all the different stakeholders to be calibrated. What does all that look like, and how does this model improve scalability and lower overall process costs?
Well, it's all about getting everyone to talk, right? Getting the designers, getting the process people, getting the SMT engineers, getting the equipment people to all understand and agree on what's the end goal. All should be sure to have and understand clear guidelines or targets for the process, right? And then, now you get into understand what's the chemistry of, the product, whether it's coating or adhesive or potting, what sort of equipment is being used, how does it work, how is it maintained, how efficient is it? And then, understand the process or if there are different techniques being used to create whatever the end result needs to be. Whether you are designing a product, again, process person, production tech, or just an operator, if you educate yourself in those areas, it helps you. It enables you to be confident and understand and define what is possible for the process. When the designers can work with the chemical and equipment vendors early in a process to talk through what they want and how they expect it to the outcome to be. This is when all of those groups can discuss any possible tripping points or roadblocks and say, wait a second, that keep out's a little too tight, or I've seen this where this caused a little too much stress on a component, or whatever it is, and you can maybe catch these conditions before it hits manufacturing and you're trying to ramp up, and then you've got an oops, right?
Yeah. No one wants an oops.
No.
Last question, Jon. Where do you see the future of dispensing technology going? And, get out your crystal ball in the next, 5 years or 50,000 years. It seems like 5 years and 50,000 years are almost the same time period in this industry.
Right.
But where do you see the future?
Yeah. Isn't AI going to solve everything?
Of course, yes. It says it is.
Everyone talks about data. Absolutely. I think, capturing data, closing the loop on processes better, maybe refining designs in applicators, easier to clean, maybe different types of designs that allow for, maybe lower cost components, easy change outs, whatever. We're seeing electronics change, and they have been, where, you're essentially printing circuits, right? 3D printing circuits or inkjetting circuits, electrical circuits, or going back to 3D printing with embedded circuitry. What's that going to look like? Will some of these protection functions go away, or will they just kind of morph into, applying them in a different manner? Whether it's smaller, lighter, thinner, faster, whatever. I don't know. I wish my crystal ball was working, but it's still in the shop.
You're wise, because these things are recorded, and whatever you say, we're going to hold you accountable to that. So I remember many, many years ago, and I don't know if this is real. I think it's real. There are some famous quotes from history that didn't age well. And one of them, I believe, was Bill Gates. Maybe it was Steve Jobs, but I think it was Bill Gates, who said he can't see any reason why anyone would need more than 512 K of RAM, in a computer. Maybe it was 640, but it was right around there. And then somewhere at the turn of the couple centuries ago, so the late 1800s, someone in the U.S. Patent Office was famously quoted in saying he believes the Patent Office will close because everything that can be invented has already been invented. There's nothing new coming. And
right.
Clearly, those didn't age well.
Yep.
It's probably best to say, I don't know.
Yeah, because, I truly don't, but, I have thoughts, and we all have ideas on things we love to see, but, not entirely sure, all of our ideas can even, come to fruition. So
that's right.
Yeah.
And things change in this industry just so rapidly. It's amazing, particularly with, like you said, the solution to all our problems, AI, is coming down the pike awfully fast. Jon Urquhart, Precision Valve and Automation, PVA. Thank you so much for being my guest today. It's great to see you. Usually you and I see each other at technical conferences. We're, sharing a lectern and, say your turn, my turn. It's good to see you, even if it's in pixel form. It's better to see you in human form, but in pixel form is not a bad second choice.
Hopefully in person, not before too long. But thanks very much for having me.
And for my listeners and viewers who would like to get more information on PVA, if you look at the show notes, if you're watching us on YouTube, look down here, and I'll have the URL for PVA and information on how to get a hold of Jon. If you're listening to this on your favorite podcast app, when it's safe to do so, of course, pull over and look at the show notes on your podcast app, and all that information will be there as well. Well, Jon, it's always, as I said earlier, great to see you, and thanks for sharing your wisdom and your expertise with me and my audience.
Thanks, Mike. Take care.
And that's a wrap on another episode of Reliability Matters. Thanks for hanging out. Whether you listened to it on your favorite podcast app or watched it on YouTube, I really appreciate you being here. If you haven't already, hit that subscribe button so you don't miss future episodes. On YouTube, give it a thumbs up and subscribe. Those 2 simple clicks really help us expand our reach. New shows drop every second and fourth Tuesday of the month, so mark your calendar. And a big thanks to PCB Chat from the Printed Circuit Engineering Association at PCBchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Got a question or an idea for a future episode? I'd love to hear from you. Just shoot me an email at mike@reliabilitymatterspodcast.com. Want to learn more about the podcast? Go ahead and head over to reliabilitymatterspodcast.com. Thanks so much for being here. Until next time, keep learning, keep doing it right, and remember, reliability matters. I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.